So last lecture we started to discuss resonances, and I introduced kind of a phenomenological approach. What we have found is that in energy momentum representation, we have this peak, which is great Wigner peak, so that unstable particle is described by this type of the resonance. So today I will do this in quantum field theory. Quantum field theory is giving consistent description of everything. So far we haven't found any kind of phenomena which cannot be described by quantum field theory. So resonances QFT, although I'm not assuming that you know what is QFT. And we consider example of production of J-psi resonance. So remember you have the plus and minus. A minus collision. This production of J-psi. Maybe not. It's like this, and then J-psi in particular can decay into mu plus, mu minus. This type of decays have also been discovered. So this is J-psi. But in general, I will consider this is applied to any kind of the resonance. So when we write the amplitude of such a process, we need to take into account all the elements of this diagram, in particular couplings here, and what is given here is the propagator of the particle. So this is, we are putting propagator. And for scalar particle, for vector particle, the propagator has some denominator of the type q square minus m square, and there is some factors in denominator. In the case of scalar particle, there is nothing. In the case of vector particle, we have g mu nu minus q. It depends on gauge you are using. But for us, what is important is this factor in denominator. Okay? So here we have production of J-psi in so-called S channel. Which means that q square equals s, and this is positive value. Right? This means that this propagator has a pole at s equals m squared. So we have s, and here is probability, or let me write for probability. So this is for the amplitude, and then for probability you will have this factor squared, right? So probability will be proportional to 1 over s squared minus m squared squared. And it has a pole at s equals m squared. So the question is what we are doing with this pole. So how we treat this. By the way, let me ask you, so at least some of you, probably now you know what are propagators, right? You just use the question of motion and you can find what is the propagator. So, how we treat this pole?
You have to make more contribution with the denominator, like an I epsilon multiplication.
You want to have this as I epsilon.
For calculation, you use the principal value.
And then? No, but then, you know, when you compute this, then P, and then go at put epsilon to 0, then you will still recover the pole.
You mean when you do the integral in the momentum, right?
Why you should do the integral? This is S, so you have the plus and minus collision, which means that you can change S. You do not do any integration. So S is fixed.
Okay.
Okay, so then you can sit down in a pole, and so cross section become infinite or what?
I see. Okay.
Is it S squared or S minus M squared?
Sorry, here is S. Correct. It's Q squared is S.
You could normalize it
What does it mean in this case?
redefining it.
And you define so what how you will redefine the mass to get the word infinity. Again, so we are in quantum field theory, so everything should be just automatic. So you need to get a correct result without any additional assumptions. So actually, this peak, at least peak, right? So that's the origin of peaks we have observed when a new particle is produced. Remember, we considered peaks in S or in invariant mass, and the particles show up as a peak. So that's the origin of the peaks observed. And now, what cuts here? So I mean, what cuts this infinity is a radiative correction. So in the lowest order, we have this propagator, right? But then we need to take into account various corrections, actually corrections to hold this diagram. But in particular, of our interest are corrections when we insert the loop here. So an example for it, for instance, in our scattering is that the loop can be formed by a plus and a minus, right? So certainly we have the couplings of this type. So we have loop of this type and also loop in the lowest order of mu plus and mu minus. So what's going on that your J psi produces a plus and minus, which then annihilate back to J psi. Correct? Agree? And of course you need to take into account high order loops. So you may have next and next order, something like this. Photon can be emitted and absorbed, or again this J psi can be emitted and absorbed. So this way I show this as a blow. So in the lowest order you have just one loop diagram, however, in high. Then you can also compute different corrections. So you have this type of the diagram, but then you need to add the diagram when there are two loops plus 3, 4 up to infinity, right? So let us make a summation of this type of the diagrams, and let's see what we will get. So this one is described by S minus M, and let me introduce 0 square, because then we will make corrections to this M 0. So that's what corresponds to the first one. It's 1 over S minus M 0 square. Now for the second one, we will have 1 S M0 squared. Then I denote the result of computation of this blow by P, so what is called polarization operator. And then we have another propagator here, 1 S minus M0 squared. Now here we will have what? We will have 3 propagators and 2 insertions of P. Summation of this series is simple. You get 1 over S minus M0, which you can put out. And then you will have series 1 plus polarization operator S minus M0 squared plus S minus M0 squared, etc. So you will have the terms which have a very simple expression, polarization operator over S minus M squared in power, some power. So summation is simple. Let me denote this. So we are computing corrections to D. So we are computing total D with corrections, which is the propagator. And then we get for D one S minus M0, and the result of summation of the series is 1 minus P S minus M0 squared. So it's series when you have P over S minus M0 in the power n, and the sum over n. And summation gives this result. Which can be written as 1 S minus M0 squared. And then you see here minus P. See, something else appears in the denominator when you do summation.
You are considering only S channel, there is other channel.
Yeah. So other channels do not produce pole. Okay, I need to add. I'm trying to deal with the pole. And this comes from the diagrams of this type. Of course, we have many other diagrams, box diagrams, corrections to blue vertices. So I'm just consider a subset of the diagrams. Okay. Now polarization operator. So this is polarization operator. Has both real and imaginary parts, and so we can write it as imaginary part, and therefore our propagator can be written as 1 S minus M0 squared plus PR. So minus minus I p imaginary. Now let us denote by m square, m0 square plus p real. So real part of polarization operator gives correction to the mass. So, and this way we very normalize the mass. And then our d is 1 s minus m square minus e imaginary part. Now cross section is proportional to moduli square of this expression. So that cross section is proportional to moduli square of d, and that will be given by 1 s minus m square plus imaginary part of polarization square. Okay, so this here have renormalization of mass, correction of the mass. Okay. Now, what is this PI? And now let us remember, let me remind what we had in last lecture. And what we had in last lecture, that according to optical theorem, imaginary part of polarization operator is given by square root s multiplied by total decay rate. So this is total decay rate. So let me again remind you of the graphic representation of all this optical theorem. So what is this PI? PI is imaginary part of this diagram. And according to optical theorem, it's given by with coefficient moduli square of this, and this we introduce k coefficient. In our case, k is square root of s. Agree? So, and remember, according to this optical theorem, what appears here and here is total decay widths, not just for specific channel. For instance, in our case, we discussed E plus and minus production of J psi. So this is specific channel and specific channel of decay, say into mu plus, mu minus. Still, the width of the resonance, or the property of the resonance, is determined by total decay rate. So now we have almost final expression. Sigma is proportional to 1 s minus m square plus s gamma square. Now, for narrow resonance, if gamma is smaller, much smaller than the mass, we can simplify this expression, because that can be written as square root of s plus m square root of s minus m So this is approximately 2 square root of S. So what we have here is, when we square this, we get the following expressions. Let me continue here. It will be, so let me continue. So if I also square this, so that will be 2 square root of S and this square root of S minus M. And then this is approximately 2M square root of S minus M. So I can put S actually here for S, and then what is staying here is square root of S minus M squared plus 1 over 4 gamma squared. So let me see if you agree. And then I can substitute something like that. So I put 1 over 4S, and actually this 1 over 4S can be substituted approximately to 4 mass squared if I'm sitting in the resonance. Okay. So what is staying here can be written as, say, 2m and then square root of S minus m. Then I need to square this, right? And then what I have here is 4 mass squared. So I reduce this to just to Breit-Wigner formula. Right?
What was the particle in the propagator?
Well, that's true for any particle, right? Because always we have in the propagator. So we did this for essentially for scalar propagator, but the same is for vector, because you have some factors in nominator which doesn't change your procedure of elimination of the pole. So bottom line is that eventually we are getting cross section as the function of square root of S, and it has this form with now maximum at square root of S equals M, and this M is renormalizable mass. Okay.
Actually, main purpose of the resonance is to determine the M.
Well, M determines the position of resonance. So important characteristic is also the width of this resonance, and the width is given by gamma. Total width is given by gamma. The same is for fermionic also, yeah, sorry.
But you are in other channels like U or T, with the distribution change.
Which channel?
Channel U or T.
No, so here we discussed
yes.
the plus and minus. Now what you want to discuss U and D, what? So just in 10 minutes we start to discuss W boson production when you have quark anti-quark annihilation. You may have some other, say like U d bar is going to W plus this channel. Now, concerning cross-section, so what is important here is the cross-section is proportional to this structure. The pole and the resonance width is determined by total decay width. However, here the factors which are staying here depend on specific channel. So here are the constants which describe specific channel in which you produce your resonance and which depends on the mode of the decay. So you may see expressions where here you have something like partial width, say with electron in our case, and times gamma mu. You can express this coupling constants in terms of this partial decay width. So specific channel gives you coupling constants in nominator. Okay. However, the resonance, or the shape of the resonance, is determined by total decay width. So you need to sum up all the channels to get total decay width.
How you determine the width from this diagram? I mean,
that's literally half, so the width of this resonance on the half of the height. It's just you can look at this formula and find what is, say, maximum, and then half of this maximum, and then just measure. You can find this from the formula, so that gamma is the width of this curve and the half of the height. So this is sigma maximum, and this will be sigma maximal over 2.
So this plot is not symmetric.
Well, I have shown this. I didn't put here anything, so it's kind of more or less symmetric, so like this. If you take into account exact expressions, that may not be symmetric. In fact, you may have also some corrections. But in this part and the upper part, it's just symmetric. Okay, so now I will briefly discuss next discoveries of particle physics, although mostly they are related already to the structure of the standard model. And so we decided to split and to put detailed discussion of these discoveries in the part of the standard model. So remember, we are in 1980 year, so 84. Further discoveries were substantially related to the structure of the standard model. Still, some discoveries we can discuss now. So the first one is intermediate bosons. Again, quite brief discussion, and you have also exercise. So remember, we discussed at low energies 4 fermionic interactions. So this is how, for instance, scattering of neutrinos on nucleons look like. And the Hamiltonian is given by G Fermi square root of 2 and the product of two currents. So this is how interactions are described at low energies. Here are specific currents. Now already Fermi had this idea that maybe the interactions are not point-like, but are mediated by some particle. So not one point in which two currents interact, but two currents interact into different points with exchange of vector boson, which is called intermediate boson, just because it mediates interactions of two currents. To describe this, we need to introduce Lagrangian of interaction of current with W boson, and that can be introduced as G2 square root of 2. So these are the factors which appear in the standard model. I just put it. This is how this G coupling is constant. And then current, alpha, and then vector field of W. Right? So what are the properties of W boson? It should be massive. Otherwise, the interactions would be long-range interactions, and you would see that this is not one point. Remember, and we can put the bound, lower bound of the mass of the W boson, and W should be bigger than the energy, maximal energy, at which interactions still look like a point-like interactions. So for beta decay, where the energies are in MeV range, the interactions look like point-like. Certainly W boson mass should be bigger than, say, few MeVs, so that these interactions look like point-like. Now, the interactions still look like point-like even for few GeVs energies. And this has been checked in neutrino scattering, for instance. And so at the energies of few GeVs, or even bigger, 10 GeVs, still interactions look like a point-like. And therefore the mass should be bigger. Because remember, 1 over m W determines the radius of interaction. And this determines the wavelengths with which we are checking this point-like structure. And therefore, if wavelength is much bigger than the radius of interaction, then the interaction looks like a point-like. Okay? So W should be massive. It should be charged. Because it interacts with charge current, and charge is conserved in the current. We introduce this that we don't want to break electric charge. So it's charged particle. And in fact, we have two W boson, W plus and W minus. It should have spin 1, again, to have Lorentz invariance. We have current with index alphas, so the field which appears here should also have index alpha, which means that this is vector-like particle. This is vector particle, like the fourth one. And finally, it should break parity. This interaction violates parity. And this is because this current is of a V minus A structure, Lorentz structure. So this interaction violates parity. It's not vector interaction. In the case of vector interaction, you would have conservation of parity. So introducing this Lagrangian, which actually interacts, describe interaction in just a single point, tells us that whole process of scattering is the second order process with respect to this Lagrangian interaction. So you have vertex here and you have vertex here. So you have 2 points in which you have interactions of this type, right? So if you write the amplitude, and again, so if you write the amplitude for the case of point-like interactions, then the amplitude is proportional to G Fermi square root of 2, right? Now, if you write the amplitude in the case of W boson exchange, we should write the following: G 2 square root of 2 squared. This is because we have two couplings. And now we need to introduce structure which is responsible for which describes W boson propagation between these 2 points. So, which means that we need to write W boson propagator. And let me again write this as Q square minus MW boson square, disregarding the factors which are staying in nominator, which are not important. Actually, this what you it depends on the gauge which you are using, and what is staying here is G mu nu, and then plus is Q nu over MW in unitary gauge. But these additional factors actually give very small contributions, and so essentially you have 1 here. Now, if you have small q square, if you have small energies, then q square is equal or smaller than S, total energy available, or UV. And this is much smaller than MW. So let us consider this limit at low energies. And then what you have here is G2 square root of 2 squared 1 over mass of the W boson square up to the sign minus, which is not relevant. So this means that G Fermi or square root of 2 equals G square 8, and here is 1 over the mass of the W boson square. So at low energies, that should be reduced to this, and therefore this amplitude should be reduced to this. And therefore, now we can determine G Fermi in terms of the more fundamental theory parameters, in terms of couplings here and the mass of the W boson. And so this is expression for G Fermi in terms of coupling constants here and the mass of the W boson. So this is what gives a dimension of G Fermi. Remember, G Fermi has dimension 1 over the mass square, and actually what is staying here, the mass of the W boson square. Now, what standard mode, by the way, what Fermi tried is to use this G equals electromagnetic coupling constant, and he got some estimation that the mass of the W boson should be 30 GeVs. This is not what is realized in the standard model. In the standard model, we have connection that E, so that G is E over sine of some new parameter which we will discuss then, so-called weak mixing angle. So this coupling is bigger, turns out.
It has to do with electroweak symmetry ratio.
Well, it is related to mixing of gauge boson, but I don't want to discuss this. That's what you will see in the particle, in the standard model course. So this parameter has been measured, and therefore this has been predicted. And therefore, when people looked for W bosons, they knew already what is G, and then they know what is the mass of the W boson. So it was not like a blind search for W boson. So it was already known when you should search for W. Let me say a few words about neutral boson. Again, so that's a genuine effect of standard model. This is what appears in the standard model. And standard model is kind of unification of weak and electromagnetic interactions. The problem is that there is no parity violation in electromagnetic interactions, and there is parity violation in in weak interactions. To reconcile these two things, so no parity violation in electromagnetic and parity violation in the weak interaction, one needs to introduce another boson. So that's what Glashow did in the beginning of 60s. So he introduced another gauge boson. By the way, again, since standard model is gauge theory, and so it's based on SU2, and one could try, because one needs to have W plus and W minus, a joint representation E3, and so it is composed of W plus W0 and W minus. So these are gauge fields in SU2 theory. But the problem is that if you want to introduce parity violation for these two guys, then this one will also have parity violation. Therefore, this cannot be identified with gamma, with photon. Right? So they are staying in the same multiplier. And if you have violation of parity for some components, then you should have also parity violation for another component. So, to reconcile these two things, Glashow has introduced another boson, which is B, which corresponds to this U1, and then managed to have mixture of this B with V0, which doesn't break parity. So that is identified with gamma. So there's a mixing of bosons here, and parameter which enters in the coupling is a parameter of mixing of B and W0. So you start with B and W0, so both are neutral. And then their mixture gives gamma and Z0. So these are states with definite masses. These states have definite gauge interactions. These states have definite masses. Okay, so this is again the same mixture procedure. And the mixing parameter, so this is 2 by 2 mixing, as we discussed already. And the mixing parameter is this theta weak, and therefore, because of this mixing, photon, which is mixture of B and VW0, it has coupling which deviates from coupling of weak interactions. So Z0 has coupling with all quarks and leptons in what we have discussed of this type. So we have fermion, like for instance electron, this is Z0. It also breaks the parity. So gamma 0 doesn't break, but Z0 breaks the parity. And it actually couples both with V minus A and with V plus A currents, in contrast to charged bosons. But the coupling is different for V minus A and V plus A, and therefore parity is also violated. So this is also massive boson, and this is even more massive than W. Again, the difference of masses or ratio of masses is connected to mixing angle. It is given by cosine of theta. But again, so all this you will study in the standard model course. So what is important for me now is that at low energies, the interactions will look like point-like. Again, if square root of S is much smaller than the mass of Z boson, this type of interactions will produce processes like scattering of fermions on fermions, and important property, there is no flavor changing neutral currents, so these neutral currents conserve the flavor, which means that in this vertex the type of the fermion doesn't change. So if you have F here, then F should be here. This is automatically actually in the standard model. Appears.
But it doesn't change flavor.
Sorry?
Why doesn't it change flavor?
Well, in general, you might have this change of the flavor, and there's a number of, say, models beyond the standard model when you have these neutral particles which change the flavor. So there is no process. You see what happens in physics, I think, in general. So everything is allowed which is not forbidden. Okay? So then in principle you can say why there is no current when you have transition of electron to muon, right? Electric charge is conserved. Why there is no coupling of Z0 which transforms electron to muon or d quark to s quark? So again, in general, if you introduce, if you have some extension of the standard model, even if you introduce more rich scalar sector, not even gauge sector, you will have such a kind of transitions.
So any process that involves a photon also have a contribution from the Z boson?
What do you mean?
Or any process with a photon, I can exchange this photon for a Z boson, but this contribution is suppressed by the mass.
So it depends on energy, because at high energies they will have equal, close, similar rates. And so another difference, of course, you have parity violation here, and there is no parity violation there. And remember, I already mentioned this when we discussed the plus and minus annihilation to hadrons. So remember, we studied the energies up to say 10 GeVs, and at the higher energies, you need to include also effect of Z0 exchange. Yes, so they will interfere with interactions. Okay, so very important discovery was discovery of neutral currents, the process of this type, and that was the first step to confirmation of the standard model, important step of confirmation. And actually, many are wondering why people didn't get Nobel Prize for this discovery. So neutral currents, again, very brief, because you will see this also in standard model course, neutral current discovery. Was in 1973, and it was at CERN, which actually produced the beam of neutrinos. They use accelerator PS, which even now is used as pre-acceleration for LHC. So there's PS and SPS, and then particles are injected in the big LHC ring. So this is PS, and it produces the neutrinos with the energy of around 1 GeV. So this peaked energy. As a detector, bubble chamber was used here. With the name Gargamel. And you can see, if you are in CERN, you can see this bubble chamber, this exposed in the outside of the building. You can, it's like historic relic. This camera is actually based on phase transition, again, we discussed in the early lectures. But here, the transition is between liquid and gas. So not droplets of the liquid was formed here, but the bubbles of gas. So the transition is from liquid to gas. So particle ionizes the medium, and you have overheated liquid, and so along the track, the phase transition starts, and the bubbles of gas are formed. So this is why it's called bubble chamber. And what they saw events of the following type, and I have the slides with these events in the bubble chamber. They saw events of the type that, so this is direction from the accelerator, and they saw events of this type in magnetic field. So this is bubble chamber, and the magnetic field is applied. So this and magnetic field is here, and they saw track, which is identified with track of electron. And the interpretation was as event when we have nu mu, which is produced by accelerator, plus electron, or to nu mu plus electron. And similar process has been observed also in antineutrino channels. So they can change polarity of the horn, which means it can select pi plus or pi minus. And these muon neutrinos are produced in the decay of pi plus and pi minus, as we discussed already in the early experiments. So these processes have been observed. Also processes of neutral current on scattering of neutrinos on nucleons. This is scattering on electrons. Questions? Now let me discuss discovery of W and Z0 bosons. That was not accidental discovery, because the experiment already was planned to discover this particle, because almost everything was known. The masses were known. By the way, these neutral current processes, which I have discussed, allow to measure this mixing angle. So coupling constants with Z0 and fermions depend on the mixing angle, weak mixing angle, and therefore the rates of neutral currents allow to measure mixing angles. So mixing angle was known, and then electromagnetic coupling is known, and then you can estimate, find everything. The masses, decay channels of W and Z. So W and Z have been discovered in 1984 at CERN. And for this, the new accelerator, synchrotron SPS, has been used. So this is proton-antiproton collider. With energies of proton and antiproton 270 GeVs each. So it's 270 plus 270. So you can wonder, why do we need so big energy to discover a particle which has mass 80 GeVs, and the mass of the W boson has been estimated as around 80 GeVs? Do you have an idea? Why still we need to have much bigger energy? Why not to just to take, say, 40 plus 40? So then you already will have square root of S, which is 80 GeVs, right? So already with much lower energy accelerator, in principle, you can produce W boson. Any idea? And we collide here protons and antiprotons. So the process which people look for is proton plus antiproton. Then you produce W boson plus the rest. It's a high energy collisions. So why do we need so high energies to? So now the square root of S is 540 GeVs, substantially high. Now remember, what is the structure of proton and antiproton? Proton and antiproton at high energies consist of quarks. Essentially, these are fluxes of quarks. So the process occurs not at the level of hadrons. It occurs at the level of quarks. It is annihilation of quarks which actually produce W boson. So what you need to have enough square root of S for quarks, for collision of quarks, not hadrons. And you remember that the probability that a given quark or parton inside the nucleon contains all the momentum is very small. So in average, at least, you have something like 1/3. So, and therefore you need to have higher energies, and you need to have a big number of these partons with required energy. And remember, the structure functions are increasing with decrease of S, decrease of X variable. And you have exercise actually to write expressions for these probabilities. So what happens is that you collide proton and antiproton, and then one of the quarks, so for instance U quark from proton, annihilates with D quark in antiproton and produces W boson. It's proton, it's antiproton. So here you have the fragmentation of the rest of the quarks. And then W boson can decay, in particular in the pair of electron and electron. So this is W plus, and positron and neutrino. Or it can also decay when you have here mu plus and neutrino. And of course you can produce W minus if you have annihilation of D quark from here with anti-U quark from antiproton. Okay? So remember, structure functions for quarks had such a form, right? As a function of X. So this is 1. And therefore cross-section, of course, will be proportional to number density of the partons with required X. And therefore you mostly produce W boson is produced by partons in this range, below even 1/3. And for this reason you need to have high energies of proton and antiproton. So what you can observe in this process. And by the way, what are the couplings of W boson? W boson universally couples with all charge currents which we have introduced, right? So you can immediately find out what are the couplings with quarks and with leptons using this. So the W boson couples universally with all charge currents of leptons, E plus, mu plus, and tau. Tau also was produced, that was observed, but this is easy to observe and identify electron and muon. So that was, the first observations are based on these channels. Now, for quarks, again, we introduced different charge currents of quarks, right? U, D, U, S, charm, S. But mostly, of course, these are not charmed and not strange. So the biggest contribution comes from these usual quarks, U and D. So you have this current, right? When U go to D. So the event,
they have then the same coupling between W with lepton than with quark?
with the same, yeah, the same coupling, remember?
Okay.
It's very universal. That's nice. It's actually also in the basis of the standard model. So all these doublets we have introduced, they have the same coupling with W. Now there were 2 experiments, UA1, and Carlo Rubbia was the spokesman of this experiment, but it also was UE2, and Carlo Rubbia and his team planned first this experiment, and the second one was created to confirm, to have 2 experiments for this important discovery. And it was a story that actually it looks like UE2 was first who was ready to publish results, but since kind of the main driving force was Carl Ruby behind this experiment, so eventually this experiment was appreciated, and Carl Ruby got a Nobel Prize for his discovery. So what has been observed? You have collision of proton and antiproton, and you have a number of secondary particles, and you will see the figures of this event, which are moving along this initial direction of collision of particles. So they are soft collisions. So the energies are very big. However, transverse momentum is quite small because of strong interactions. Strong interactions are soft in a sense. But suddenly you have the track of electron, which kind of go substantially outside of this bulk of the secondary particles, or muons. Also events with muon have been observed. So just single electron, single muon. And therefore the signature of reduction of W boson is appearance of this electron. And in the case of decay of W boson, so typically this what we call transverse momentum, and transverse momentum is determined as projection of momentum of particle on the perpendicular plane. I think we have already discussed this a little bit. So typically this will be mass of the W boson over 2. So what happens is the following. W boson is produced. It decays into positron and neutrino. You do not see neutrino, but you see just electron. And you see also kind of disbalance. So there is no visible momentum conservation in this plane, right? So you have some big momentum transfer moving in upper direction, but there is nothing here, which is due to neutrino, of course. So what has been measured is distribution of number of events as the function of transverse momentum of lepton, charge lepton. So it has typically the distribution of this type. It was of course predicted. So this is mass of the W boson over 2. And there were some events above this because W boson mostly produced at rest. But still there are some events when W boson is still moving, and therefore it can produce charged leptons with momentum which is bigger than mass over 2. So this has been predicted and observed. Also people measure the angular distribution of electron or positron, and in this way you can check actually V minus A nature of the current. So angular distribution is given by Lorentz structure of these vertices. And that was another confirmation of V minus A interaction. Questions?
Couldn't it be discovered with the electron-positron collision collider?
Well, if you have electron and positron, you need to collect something which is charged, right? So in E plus E minus, well, at least not in annihilation, because if you have E plus E minus annihilation, you produce some neutral particles. Z boson can be discovered, but not this. Or you can produce pair of W plus W minus. Right? If you have E plus E minus annihilation, so the process can be like this, for instance. E plus, E minus, and you produce W and W, which is neutrino. So you can produce in this way. But of course this is less probable, so that, and you need to have a high energy accelerator. That has been realized at lab later. Okay? Now Z0. That 0, the story is even simpler. Why it is simpler? So you have similar process, but now you need to have annihilation of the same type of quark and anti-quark U, and say U bar. You please show another diagram, but I just use this one. So U and U bar in proton and antiproton can annihilate into Z0, and then in the final state you have E plus E minus or mu plus mu minus, right? So the diagram is you have Q bar annihilation into Z0 with the decay of, for instance, E plus E minus. Again, you need to take into account, computing the cross-section of this diagram, you need to take into account distribution of quarks or this Bjorken variable X.
But this process, for example, is also possible with a photon. How do you differentiate from the others?
So it's also possible, and the photon gives the background, and therefore what has been observed, exactly, so I have here gamma. What has been observed is the following. But let me first say how the event looks like. This type of event looks like production of electron and positron with large transverse momentum. So that the event is of the following type. You collide proton-antiproton. Again, you have a bunch of the particles in the second, in the final state, and then you have now two tracks, E plus and E minus, or mu plus and mu minus. So if Z0 is at rest, then it should be along the same line, but that type of the configuration reflects that the Z0 moves slightly. Okay? So what you can do, you can measure the invariant mass of E plus and E minus, and you can construct the distribution over invariant mass of E plus E minus. Number of events as the function of invariant mass. And then what you see is precisely background due to gamma, and this background looks like so contribution, not background, the contribution is falling down like this without any structure, because for photon, if you want the resonance, is at 0. And then you have peak and the mass of the double Z boson. And the mass of Z boson is 92 GeVs approximately. So it's heavier than W boson. So, and also width has been measured, but more precisely, width has been measured in plus E minus in at lab experiment. Or more precisely, it's let me put so 91 and 2. It's 91.2, and mass of W boson is 82 GeVs. So later, lab experiment, electron-positron collider has been constructed. The same ring as now LHC operates, and it was detailed study of the processes, in particular of production of Z0. So now it's E plus and E minus are colliding, produce Z0, and then Z decays. Here, no need to have so high energy to be in resonance. It's enough to have the energy which is half of this. So 46 GeVs should be the energy of each of the beam to produce, to sit down in the resonance of Z0. So and it was very precise measurement of resonance curve, and it has been found that the width of Z is 2.49 GeVs. So inverse gives a lifetime, and you can find that the lifetime is close to 10 to the minus 25 seconds. So you do not, of course, measure I don't know, propagation of Z0, and it shows up as a resonance. So the total width, so this is total, is given by visible width plus invisible width. So what is this invisible width? This is due to decay of Z0 into two neutrinos. So you have the mode of the decay of Z into new bar. So you do not see these neutrinos. However, remember we discussed that the resonance width is determined by total decay width. So you need to take into, although you do not see gamma, however, the width is determined by all the channels, including neutrino channels. So in this way you can measure what is this invisible width, and this invisible width is proportional to number of neutrino species. In this way it has been established that we have 3 neutrino species, not 4, for instance, that is excluded, and not 2. So this invisible width has been measured, and the data are in a good agreement with the number of neutrino species, 2.98. So the accuracy is so big that even this deviation from 3 can be seen at 1 to sigma level. Questions?
No.
So that has been established by a lab experiment. These precise measurements of widths of all the parameters of Z0, different modes of the decay. Questions?
Can we use radiative correction arguments to define a renormalized mass for the photon?
But at the end is 0.
Well, it's 0, yeah.
Still 0 is
Due to gauge invariance, so the corrections are 0. Two more discoveries. So let me mention discovery of top quark. Actually, Giancarlo is working and studying top quark at LHC, production and properties of top quarks. So you can ask him many details if you are interested.
You have to get some problems for that.
What?
You should include some exercises.
Yes, yeah, you have some exercise to check. So what is this top quark? Top quark as a member of third family of quarks has been introduced by Kobayashi and Maskawa. So we have top and bottom and the doublet, and they form charge current interactions. And it was a long story about discovery of top quark. The point is that mass of the big quark is around 4.2 GeVs. And as it is in other generations, one expects that the mass of the top quark should not be very much different from the mass of B. Maybe 2 times difference or 3 times difference, something like that. Actually, the difference between S quark mass and charm is bigger. It's almost like an order of magnitude. But anyway, even if this mass is order of magnitude bigger than mass of B, you would expect top, let's say, with mass of 40 GeVs. And in fact, there were some kind of announcements that people see top quark at the energy, with the mass about 40 GeVs, but then that was renounced. So what is amazing, the top quark is really very heavy. So it turned out that the mass is around 175 GeVs. So this is the heaviest particle actually we saw. And this mass is produced by Yukawa interactions with coupling 1, which probably is not accidental. Now, top quark has been discovered at Pevatron in the US. In 1995, although discovery actually lasted quite a lot, so they have already data, but the analysis is extremely difficult. So they use Tevatron, which is proton-antiproton collider, and the process is production of top anti-top quark plus X. And top decays so quickly that it has no time even to form hadrons. So no sense to speak about hadrons with top quark inside. So it already decays before forming any colorless structures. There are two experiments in this discovery. One is CDF, and another is D0. One of the channels, and there are several different channels of production of top, is the following, is quark, so production. Is quark-anti-quark annihilation. So you have proton, antiproton, and then you have quark from proton and anti-quark from antiproton. So they annihilate into gluon. This is gluon, which then produce pair of top bar. And then you have the rest of the particles. Quarks which fragment into hadrons. So there's another channel of production which is gluon fusion. This is the process when one gluon from, say, proton interacts with another gluon from antiproton, and then they produce again top bar in such a process. So this is gluon, and this is gluon. And here you have the rest of the particles. So now two gluons are transforming into top anti-top. So discovery was based on essentially mostly production of top in this process, but later also production of single top has been observed, and in this case you have annihilation of U and D antiquark into W, say plus, and then W decays into top and B bar. Okay, through W boson. So you produce top, anti-top, and then they start to decay. They decay quite quickly. So let me delete this. Okay. So I produce top, anti-top. Have top plus, top minus, and then decay due to charge current weak interactions into B plus and W minus plus B minus and W plus. This is just due to charge currents because top has this coupling with B and W boson, forms the current with HEP-PP methods. Now, W boson, in turn, can decay into neutrino and charged lepton, or into quark-antiquark pair. And here's again neutrino, lepton. So this is plus, and this is minus. And then here it should be antineutrino, or into again quark-antiquark pair. And then you have different possibilities. Actually, 4 different possibilities. When you have in final state quark-antiquark here and quark-antiquark here, or you have 4 leptons, or you have quarks and leptons pairs. So you have 4 different combinations of final state, and experimentalists have studied all these combinations. And then experiment was actually planned in such a way that they were able to identify the products of the decay of B quarks. And so they created some specific detector, because lifetime is small, but they managed to detect the products of decay of B and reconstruct invariant mass to be sure that this B is produced. So what they did what is called B tagging. So to say, they selected events, only those in which they're sure that B and B bar are produced, right? Because in this chain of decays, you need to have appearance of B and B bar. And now can you imagine that they measured the products of momenta or energies of all these particles to reconstruct invariant mass of top and anti-top. So you can imagine how sophisticated should be measurement, how complicated should be detector to measure and identify that you see, say, lepton, you have missing energy due to neutrino, identify the energies of quark jets, and momenta of these jets, and reconstruct eventually invariant mass of these products which originate from decay of top. And it's a mess because you have top and anti-top, so you need to separately measure the products of decay of top and anti-top. So eventually what has been constructed is an invariant mass of products, a number of events. So which means that if you just take this, you need to measure B. So for instance, invariant mass of B, quark, anti-quark, or invariant mass of B, neutrino, and charged lepton, and then the number of events look like here, and then the maximum corresponds to the mass of top. So the mass of the top is 173 GeV. Well, also it's kind of non-trivial to define what is the mass of the top particle so quickly decays. Questions? So they saw some events, but then they analyzed during several years, just analysis of the events took so long time to be sure that this is a decay of top.
Could you repeat how they managed to collide this top anti-top?
How they
managed to collide this top anti-top?
No, it's not top collider. So this is decay. So this, remember, I have written, this is not decay. So we have just a system of produced top anti-top. So what they did again, this is gluon fusion, for instance, right? I have written this diagram already deleted, right? So for instance, you have this type of the process, gluon fusion, and then you have top and top bar, right? So plus and minus. And so I just here discuss decay of this system. But of course you have here also a mess because there is a number of secondary particles in the fragmentation of quarks and gluons. So again, what they have is collision, and then a lot of, because the energies, this is tevatron, this is 2 TeVs energy of collision, and you have huge number of secondary particles. And then among these particles, you need to select something which corresponds to big quark, which actually is not even moving far from this, but then you may see some charged lepton, I think I have somewhere, and then have some high PP jets, which then identify it from these quarks, from decay of W boson. So it's a many-step procedure. So you see some jets, then you imagine that they can come from W boson, so you construct the mass, invariant mass of this quark, be convinced that it comes from W boson, then you reconstruct the B, its invariant mass, then sum up everything to get this type of the distribution. You can ask Giancarlo how they are doing this at LHC. So at LHC they have a lot of these events. Finally, I will discuss discovery very shortly, tau neutrino. Nobody was in doubt that tau neutrino exists, and nobody wants to give Nobel Prize for this discovery. So remember those discovery of electron neutrino, muon neutrino, and those were awarded by Nobel Prize, but not tau neutrino. So tau neutrino was discovered, so a new tau discovery. In year 2000, and that was in Fermilab. The experiment had the name Donut, which stands for detector for observations of new tau. So this is detector for observations of new tau. Donut. So again, the idea is to produce new tau in some space point and then detect its interaction in another space-time point. So people use proton beam, which hits the target, and then tau neutrino was produced, and then in the detector they observe the interactions with production of tau lepton and the decay of tau lepton. So as the detector, what has been used nuclear emulsions, and the plastic scintillators. Now let me give you a few details about the production, so how these tau neutrinos were produced. The important thing is that as a target people use very heavy material and dense material, and actually they use tungsten. And this is to organize beam dump experiment. So to say, in this way, they use this dense material to absorb all the secondary absorb usual secondary particles like pions, K mesons, because they have quite long, relatively long lifetime, and so most probably they are just absorbed. And only those particles which have very short lifetime have time to decay before absorption and losing of energy. So the idea is to use proton colliding with the target and production of DS meson and everything else. DS meson has a mass slightly bigger than the mass of tau lepton. So that DS can decay with emission of tau and new tau. And then tau itself decays with emission of nu tau and x. So one of these should be anti-tau neutrino, another is tau neutrino. So in each of these processes you are producing nu tau and nu tau bar. Now what is this ds? I think I have written what is the mass of this ds. ds is the meson which contains charm quark and strange quark. So ds is the system of charm quark and s anti-quark. And the process is that these two annihilate. This is charge current. And then W boson produced in this way. Virtual W boson decays into tau plus and nu tau. So the mass of this particle, m ds, is 1068.49. Actually quite close to the mass of the tau lepton. Remember, tau lepton has a mass 1.777 GeVs. So the phase space is not big, but this is kind of optimal for the process of production. Now what happens in the detector? Nu tau interacts with nucleon, produce tau lepton and everything, and then tau lepton can decay in the modes we have discussed into nu tau, nu e lepton, or can decay hadronically into nu tau and the system of hadrons. Finally, what is the observation? What was observed is so-called tracks with kinks. So what is that? And these are emulsions. So what's going on? They expose emulsions during some period. Then they develop these emulsions, and then they saw the tracks which appeared in these emulsions. By the way, the energy of protons was quite high. It's 800 GeVs. And it is not accidental. First you need to produce this ds, but also you want to produce tau neutrinos with high energies, high enough, so that they will in turn produce tau leptons for charge current. So the observations are the following. You have neutrino, which is in the detector, produces tau lepton and some hadrons here. So tau neutrino interacts with nucleon. Then emulsions allow to see the tracks of tau leptons. So all these quite small, it's millimeters or sub-millimeters, but then you expose and you see, using microscope, you see the track of this tau. And then you see decay of this tau, and tau decay, for instance, into two neutrinos and electron. So what is observed in this event is one point of course you do not see neutrinos when neutrino is coming from here. So you see one point of the interaction, a track of tau lepton, and then the track which has this kind of broken form, so which actually corresponds to decay of tau into electron. So this is track with kink, and this is the signature of this of such an event. So this is one type of the event which has been observed. Actually, two events of such a type has been observed in the first series of the experiments. But also the events when you have decay of tau hadronically. So again, you have tau lepton, which decays with hadrons. And then you have here some secondaries in the first interaction. So the track of this type. And actually, in the initial series of the experiments, two events of this type have observed and two events of this type, and on this basis it was claimed that tau neutrinos were eventually discovered. I haven't discussed Higgs decay, but this is really what should go into standard model course. Questions? But if you want, I can next lecture mention a little bit, say something. Actually, in previous years, I had more lectures, and I discussed in details discovery of Higgs boson. But so now it's we move this to standard model course. Questions?
So what's the idea in the discovery? Just they can determine that if we see these skins, then necessarily there has to be a neutrino. Is that the idea?
Yeah, yeah. Remember, we had some criteria of what is discovered of neutrino. You need to produce this neutrino in some space-time point, and then to see interactions at another point, and to see and prove that you have transfer of energy, momentum, and quantum numbers. So that certainly this type of event can come from interactions of neutrinos. Okay.